All right, so for these last two, we could try what we did at the very beginning, just plugging in 2. But you notice if you plug 2 into this function right here, it's going to give you a 0 in your denominator. That's a problem. So what we can do, though, we can factor this thing. The bottom is really easy to factor. It's a difference of perfect squares, t plus 2, right? And then t minus 2. Forgive me for my t's looking like plus signs. All right, and let's factor the top. I know that I bet my bottom dollar since since 2 was a problem area, I'd really like it if t minus 2 was a factor of this, and I really feel like I can rely that it is. In fact, I just know that it is. And here's the other thing: the other factor of this is t minus 1. Here's why you should assume that this happens. We want to take the limit as x approaches 2, but t minus 2 is a problem. Well, these problems will pop up. You'll see them on tests, and it'll just magically happen. They're set up so that the the bad thing gets removed. We call this removing a discontinuity, but you don't have to necessarily know about discontinuities yet to do the algebra. Now, here's the idea. This function behaves a lot like what's left, t minus 1 over t plus 2. Now we can plug 2 into that. If you plug a 2 into this t and this t, well, now what you get is 2 minus 1 is 1, 2 plus 2 is 4, so you get 1/4. Let's do the same thing here. Again, let's factor. The top is actually not something you need to factor, but here's the thing. The bottom, man, it would be really nice since we want to have x approach 1. It'd be really nice if x minus 1 was a factor. Well, in fact, it is. And that's what it factors the denominator here. These cancel out. You get the top doesn't become 0. Here's the thing. These cancel out to like 1 and 1. That's what happens when things reduce or cancel. So it's 1 over x plus 1. Well, now we can plug 1 into this thing without causing a 0 in the denominator. You get 1 over 1 plus 1 is 2, so 1 over 2. So this answer is going to be 1/2 right here. Now let's look at vertical asymptotes. Remember, vertical asymptotes happen whenever your limit as x approaches infinity is equal to a particular number. So if you have, oh, sorry, it's a, apologize, that's a horizontal. Whenever your limit as x approaches some particular value of the function is equal to infinity. So it's when you have this happen. If you want to look at it graphically, it's when you see something like that happen. Okay, and they actually can go both up or both down, but a lot of times one will go up, one will go down. Here, the way to see it algebraically, though, is just make your denominator equal to 0. So vertical asymptote happens when you divide by 0. That's another way of thinking it. What's my denominator? X plus 4, set that equal to 0. What's the solution? X equals -4. Boom, that is the equation of your vertical asymptote. Remember, vertical lines are x equal line. This one right here, well, there's 2 if you factor it. Let's do 1 over, you have x plus 3, you have x minus 3. And so here's the thing, you get 2 vertical asymptotes, x equals 3 or x equals -3. Now you might think, oh, well, it's obviously the same thing for the last one, but here's the problem. When we factor this, yeah, we get x plus 3, all right, and then we get x minus 3 here, but x plus 3 is also a factor of this. So even though there is still a little tiny pinhole, there's a problem. Still can't put 3 in here, but the vertical asymptote kind of cancels out. So here, the only vertical asymptote is x equals -3 because the other one just kind of reduced or canceled out. All right, that's it for the study guide. Good luck on your